two different things to be able to do this. One of them is zero product. That's this. Zero product property tells you that if you have two things multiplied together and they come out to be zero, then one of them has to be zero. This extends to more things. If you have 10 things multiplied together and the result is zero, then one of the things has to be zero, one or more. It could be multiples of them. But if you just think about it, this should make perfect sense. If I take two things and multiply them together and neither one of them is zero, I clearly cannot get zero. So if I get zero, then one of them has to be a zero. So that's all the zero product property says. And for such an innocuous, kind of obvious, if you just think about it, statement, it's actually quite powerful. We end up using this quite a bit, actually, in math in general. We're going to use a little bit here, but you'll use it more in calculus and more as you go further on. So I want to show you how we use it. And the basic way is, if we have a polynomial equation, so this is already factored out. So if we have a polynomial equation, we can move everything over to one side so that the other side is zero, right? We just add or subtract whatever we need to get everything on one side. Then the other side is zero, and then we factor. And when you factor, notice this stuff is not being added together anymore. Now it's being multiplied. And so I've got two things being multiplied together that equal zero. So I know that one of them is zero. And so that's how you solve these, is you set the individual pieces equal to zero once you have it all factored out. So let's just finish this one. This one's actually pretty much done. Almost all the work here is the factoring. So this says that 2x minus 1 equals 0, or 5x plus 11 equals 0, plus 11. Oop, that's a sloppy x, but whatever, equals 0. Then you just solve. Add 1 divided by 2, x equals a half. Subtract 11 divided by 5, x equals negative 11 over 5. And so that's what you end up with for your solutions. So once you have the polynomial factored out and set equal to 0, you're basically home free. It's super easy, right? And so, yeah, that's pretty much how you want to do it with the zero product property. Now, there can be a lot of work involved with factoring, right? Like, factoring is not always easy, and sometimes it's not even possible. Now, in this next example it is, but this doesn't always work. So I would caution you against spending too much time trying to factor something to solve it as a quadratic equation. If it works, it's the easiest way. If it doesn't work, it can be frustrating. So, like, if you're trying to factor something and it's not working out, just do one of the other methods that we'll get to in a second. So anyway, here's my second example, right? So I got x squared minus 3x equals x plus 12. Now, you might think to yourself, aha, I'm going to factor an x out of the left side, but you should not do that. What you want to do is it's this part that's super important. You want it to equal 0 before you start doing anything else. So the first thing I'm going to do is I'm going to move the x and the 12 over to the left, right? So I'm going to subtract x and subtract 12 and put them over here, minus x minus 12. That's a little tight there, sorry. And then we end up with x squared minus 4x minus 12 equals 0. And that equals 0 is the key component. Now, I'm looking for two numbers that multiply to be 12 and add up to be negative 4, or multiply to be negative 12, I should say, and add up to be negative 4. I'll let you work on the factoring, but it's minus 6 and 2 is what I want. So I should write this as x minus 6 times x plus 2 equals 0. And if you multiply that out, you'll see that that does, in fact, give me that thing that I've got over there. And then I just set each piece equal to 0. So x minus 6 equals 0, or x plus 2 equals 0, right? And this, so I get x equals 6, or equals 6, or x equals negative 2. So again, the solving the quadratic equation part is not at all hard here. The hard part is the factor, right? That's like 90-ish% of the work here. So make sure you're good at factoring, and then this stuff is pretty easy when it works. All right, let me show you the next kind, which is completing the square. And I've got my diagram all drawn up so you don't have to sit here and watch me do it. But the basic idea is that you try to transform a quadratic equation into this form. That's what we're looking to make. So here's the way I'm going to do that. I'm going to ignore the k for a second. We'll come back to it in a minute. I want to look at the left side, and I'm just going to multiply it out. And when I do, the thing that I get is effectively this, right? So I'm taking, I have a square here. It's supposed to be a square if I'd drawn it better. Each side is x plus h long. So I'm doing x plus h times x plus h, right? Which is what I'm doing here, x plus h squared. And I'm saying that the area is equal to k. Well, x plus h squared is x squared plus 2hx plus h squared, right? You can see it literally from the picture, right? X squared, there's an hx, there's an hx, and there's h squared. And each of these is representing the area, right? This big square here is x by x, so its area is x squared. This medium-sized rectangle is h thick by x tall, so its area is h times x, so it's this one. And then this area over here is h by h, so it's h squared. So this comes out to be x squared plus 2hx plus h squared equals k. Now, I want to highlight this. That is super important, this 2h right here. This is the thing that you really want to concentrate on when you're making this. So let me show you how to go about essentially crafting this form, right? I'm sort of working backwards here, right? We're not going to, like, our end goal is this thing I started with, and I'm showing you how we're going to get to it. So ignoring the k for a second, if I look over here, I can figure out what h squared should be by knowing what the coefficient of x is, right? Whatever is here is 2h. So I divide it by 2 to figure out what h is, and then I square it to figure out what h squared is. So if I have something like, let's say, x squared plus 8x, I can figure out what I would need to add in order to make this a perfect square. So if 2h is 8, then h is 4, right? So let's write that down. 2h equals 8. So h equals 4. And h squared then is 16. So that means if I were to add a 16 here, now this thing is in that form, and I know that it factors like x plus h squared. And because I know what h is, right, then I know that, let's set this equal to k, that this left side factors as x plus 4 squared equals k. And so you might ask yourself, well, that's great, but like, in what situations can I actually do that? And the answer turns out to be all of them, which is why this is great. So let me show you one, and I will show you how we go about doing that. So here is a random quadratic equation. Let's do that thing I said. I want to figure out what needs to be added here to make this a perfect square. So the first thing I'm going to do is I'm going to clear out that 11. I don't really want it there. That's going to be my k, actually. It's going on the other side. So I'll add 11 to both sides, and we'll get x squared plus 6x equals 11. All right. And now my left side is in that form I just had, right? This is x squared plus 2hx. So what I have here is that 2h is 6, so h is 3. And h squared is 9. That means that what I should do is I should add 9 to both sides of the equation. And I can do that because it's an equation. I can do whatever I want, right? So this is not as intuitive as trying to solve for something, right? I'm not just peeling stuff off to be left with an x. I have to know what I'm trying to construct and build it, essentially. And so that's what I'm doing here. I know what h squared is. I know that what I want ends up being like this, right? So I just figured out this piece, and I didn't circle that very well. I just figured out that piece right there. So what I'm going to do is tack that piece on. Now it's an equation, so that's okay. If this was just an expression, I'd have to do something different. 9 equals, well, 11 plus 9 is 20. All right, So now I can factor my left side. So the left side I know factors as so I could try and factor it, but I'm not going to because I know how it comes out. I don't need to like do some work to factor it. I know it's this x plus h squared on the left, which is why it's so important to know what h is, because then it's easy to factor. And you might say to yourself, I mean, I can factor x squared plus 6x plus 9. That's no big deal. This step. I'm doing an easy one first here. This step is surprisingly hard. It is really messy sometimes. So I know that this comes out to be x plus 3 squared equals 20. Now, I'm going to do something that I wish I had reordered the topics a little bit, and maybe you want to go look at radicals and simplifying radicals before you do this, but here's the basic idea. What I'm going to do now is take the square root of both sides. So the reason I'm going to do that, actually, I'm going to make another page here. The reason I'm going to do that is the following. If I have something like x squared, excuse me, not plus, I mean x squared equals 9, that's pretty obviously 3. It's less obviously negative 3, right? So the negative 3 also works in that equation. So when I take the square root of both sides, which is how you cancel out a squared, I have to have a plus or minus because there are two correct solutions to this equation. So I need to say that x equals 3 or x equals negative 3. Now we have a shorthand for that in math, and it's this, because this comes up quite a bit actually. So can I go back to, if I can't specify the page, I have to click all the way through. All right, you can see some of my examples. So that's what I'm going to do here. So I'm going to have x plus 3 squared is 20. So I am going to take the square root of both sides. And again, that's a thing I can do because this is like I'm doing the same thing to both sides. So the left side is x plus 3 because the squared and the square root cancel. And the right side is plus or minus the square root of 20. Now, I'm not going to harp on this too much. This is a thing that I wish I had shown you earlier, and that's what I was saying. Like maybe you want to go look at simplifying square roots, which I put at the end of the course, which was a mistake. But basically, what I'm going to do here is this. I'm going to think of what's the biggest perfect square that's in 20, and it's 4, right? So 20 is 2 times 2 times 5. And then I'm going to rewrite that like this, which is legal. You can do that. And the square root of 4 is 2, and the square root of 5 is whatever. It's about 2.2 or something like that. I don't care what that is. And this is 2 root 5. It's 2 times the square root of 5. There you go. Now I will say this. I'm actually not that worried about you simplifying your square roots right now. You should do it. It'll make things easier and neater and just generally look better. But because we haven't spent much time on it, I'm not going to worry about that until a little bit later in the course. So please do it if you can. But basically what you're looking to do is take the largest perfect square that is a factor of the number under the square root and write your square root like that. With the largest perfect square times whatever you have to multiply it by. So let me just do a quick example, another quick example, like the square root of 48. So 48. So here, let me show you how to find the largest perfect square, because it's not obvious, right? So I'm going to do a factor tree. I think I've shown you guys this before. I must have. And then I'm going to look for pairs. So I got a pair of 2s and another pair of 2s. And so that means that all of these 2s paired up with something. And so they're all going to be part of a perfect square. So this is, so 2 to the 4th is 16. So this is going to be the square root of 16 times whatever's left over, which is in this case 3. which is the square root of 16 times the square root of 3, which is 4 root 3. One more. So, I don't know, square root of 84. 84, 2 times 42. And by the way, when I'm doing a factor tree, I usually take out the easiest stuff first, because it's easy to know that 2 goes into 84, and it's easy to divide 2 out of 84, and it makes the number smaller so that I get closer to something that is more recognizable, right? I'm guessing you probably don't know the prime factorization of 84 right off the top of your head. So the trick is to pull out easy stuff until you do, right? Until you get down to something you do. So this is 2 times 21, and 21 is 3 times 7. So I'm looking for pairs, so I got a pair of 2's. So this is the square root of 4 times 21, which is 2 root 21. Want to do one more? One last one. So let's do the square root of 150. Yeah, that's a nice, decent one. Square root of 150. So again, I'm going to do the exact same thing. I'm going to take out something easy, which is a 10, right? Well, 150 is clearly 10 times 15. Taking out whatever is most obvious. 3, 5. I got a pair of 5s here with a 6 left over, right? 2 times 3 is 6. So I'm going to rewrite this. That pair of 5s is 25. So this is 25 times 6, which is root 25, times root 6, which is 5 root 6. So anyway, that's how you can simplify your square roots. That'll become more relevant to us in a few minutes here. We do quadratic formula. Yeah. So back to where we were, in case you've forgotten, we've got x plus 3 is plus or minus 2 root 5. And then all I have to do from here is solve for x, right? So I just subtract 3. So x equals, and now again, let me emphasize this here. You don't want to say that this is 2 root 5 plus or minus 3. That's incorrect, because this is plus 2 root 5 or minus 2 root 5. So the plus or the minus stay with the 2 root 5, not the 3. Right? So this is going to be negative 3 plus or minus 2 root 5. And if the plus or minus is throwing you off, feel free to write that like x equals minus 3 plus 2 root 5. X equals minus 3 minus 2 root 5, because that's what it means, right? Those are the same thing. It's just this is the shorthand. So this is really 2 solutions, and they are both radicals, right? There's nothing, they're not integers, not particularly nice solutions. This one's not particularly bad. There's no fractions or anything. So let's see one that is. This one is going to be a complete mess. I'm sorry, I meant to say this equals 0. I apologize. Okay, so what I'm looking to do is figure out what I need to add to make that a perfect square. And you might notice that originally I've just got x squared. No coefficient here, just x squared. So that means that when I am solving this, I have to do that, right? That has to be the point I am starting from. So we're going to get some nasty fractions here. And sometimes that just happens. And there's really not a nice way you could, like, in equations, a lot of the times you get fractions, you can multiply both sides by something to make it work out nicely. Not here. You just get fractions and they're bad. So let's do a bad one. The first thing I'm going to do is I'm going to divide everything by 3. Actually, I guess I'm going to move the 1 over first, and then I'll divide everything by 3. So I'm going to subtract 1 from everything. We'll get 3x squared minus 5x equals negative 1. And then I'm going to divide everything by 3. So I'm dividing both sides by 3, but that means doing each term by 3. So I've got x squared minus 5/3 x equals negative 1/3. Remember when I said, well, 1, sometimes you get nasty fractions, and here we go. But 2, you don't want to try to factor the thing that you make. You want to know how it factors. And that is going to be really important here, because when we get to trying to factor this thing, you're not going to see how it goes, right? Like if you tried to factor it just without knowing where it came from, it would be very hard. However, once you know where it comes from, it'll actually be not that bad at all. So the thing you want to notice here is that minus 5/3 is 2h. Right? And so I need to divide by 2, or I'm going to think of it as multiplying by a half in order to get down to just h, right? So I'm going to go times a half times a half. Half times negative 5/3 is negative 5/6. And over here, I just have h. So if h is negative 5/6, then h squared is going to be 25/36. Notice that it's positive because it's always positive because you're squaring something. So you always get a positive number here. But that's my h squared. And that's the thing I need to add to both sides, right? Not a thing you'd think of just off the top of your head. You really have to know what you're building and kind of build it using this strategy. All right, so that's what I'm going to do. I'm going to add 25/36 to both sides of this equation right here. So I'm going to get x squared minus 5/3 x plus 25/36 equals, I'm sorry, my portrait's in the way here. I don't think it moves in the video when I move it here, but it's kind of annoying when it's in the way. So that equals negative 1/3 plus 25/36. All right, I'm going to do 2 steps at once here. Step 1, I'm going to factor the left side. And if you looked at that and said, I have no idea how that factors, that's a bunch of nasty fractions. It probably doesn't even factor. Turns out it does, and it factors as x plus h squared because it always factors as x plus h squared. That's what we made, right? We're deliberately forcing it to factor like this. So you don't need to try to factor it. It's going to factor like this because that's how we're making it. So I know what h is in this case. H is negative 5/3, or excuse me, h is negative 5/6. So this is going to factor as x minus 5/6 quantity squared. On the right side, negative 1/3 is negative 12/36. 36 and plus 25/36. Negative 12 plus 25 is 13. And now I'm in that form. I've got x plus h quantity squared equals k, right? The h is a little messy, but it's still the same thing. So here I'm going to take the square root of both sides and say that x minus 5/6 equals plus or minus the square root of 13/36. One thing you can do with square roots is you can split them up top and bottom with fractions over fractions. So we end up with plus or minus root 13 over root 36. And the reason I do that, of course, is because the square root of 36 is just 6. So we end up with x minus 5/6 equals plus or minus the square root of 13/6. Add 5/6 over, and then we're done. There you go. So you can see that this method solves any quadratic equation. Literally all of them can be solved this way because you can always construct a perfect square out of something that looks like this by figuring out what h is, squaring that, adding it to both sides of the equation. So this is pretty neat and actually really powerful in my opinion. Being able to solve literally every quadratic equation is great, right? That's quite powerful, but it doesn't put a lot of limitations on you. It's nice. The solutions aren't always nice. Sometimes they look like this, and that's just what the solution is, or what the solutions are, I should say, and that's just how it goes. Let me show you one more, because there is a situation that we could run into that is not covered yet. So let's say I didn't set these equal to 0. What a turkey I am. These should all be equal to 0. Okay, so I got t squared plus t plus 1 equals 0. So I'm going to do the same thing as before, subtract 1 over t squared plus t equals negative 1. So my coefficient of the middle term of t here is a 1. So what I've got is that 2h equals 1. So h is a half. And h squared then is a fourth. right? Half times a half is a fourth. And so I'm going to add a fourth to both sides. And so I get t squared plus t plus 1/4 equals -1 plus 1/4. -1 plus a fourth is 3/4. -3/4, excuse me, 3/4. And we're off and running. So left side, again, you might not think to yourself, aha, I know exactly how that factors. But you can, right? Because it's going to be x plus h quantity squared. That's what we're making. So that means that, or t plus h in this case. So we're going to have t plus 4 quantity squared equals -3/4. And perhaps you have spotted the problem here that we're going to have, which is now I'm going to try and take the square root of both sides. And when I do on the left, it'll work fine. I'll get t plus 4. On the right, I'm going to have this plus or minus the square root of -3/4. And you can't take the square root of a negative number without knowing complex numbers. Now, I often want to include complex numbers in Math 107. I don't think they're too hard for you to handle, but I didn't include them here, or I didn't include them in this course. Maybe I should have, but I didn't. And so I'm just going to cut this one off and say that there's no real solutions to this equation. So there are no real solutions to this equation right here. There are complex ones, right? You get complex numbers, but we're not worrying about those. I'm just going to say no real solutions. So we're going to say no real solutions. That doesn't mean that there are no solutions, by the way. It just means none of them are real numbers. And I want to show you what that looks like in a graph. And I just realized I don't think I have that open. Yeah, I'm gonna pause the video for a second. All right, I got my Desmos open. So here's what I'm looking at. So this is the graph of y equals x squared plus x plus 1. It's this parabola right here. And the thing you might notice here is that if you have, if I replace this y with a 0, that's the equation I had, x squared plus x plus 1 equals 0. That's the same thing as finding the x-intercepts of this graph. If you think way back to when we were finding intercepts, that's what you do to find x-intercepts, is you set y to 0. So the y-intercept, or excuse me, the x-intercepts of this equation here are the solutions to the equation that I had, the x squared or t squared plus t plus 1 equals 0. And if you look, there aren't any, right? So we're looking for something that doesn't exist, and so there aren't any, right? So there's no solutions. That's why you get something that looks like this, where it has no solutions, or it has no real solutions, I should say, because, well, they just don't exist, right? I'm looking for the x-intercepts or the t-intercepts. If I had y here, and there aren't any, so I get this. Let me go back a second to show you. Let's say this one, right? X squared plus x minus plus 6x minus 11. So this does have two intercepts, right? These were real. So let's see what that looks like. So if I do y equals x squared plus 6x minus 11, you can see there they are, right? This does have two intercepts. This is -3 minus 2 root 5, and this is -3 plus 2 root 5. Right? If I do -3 minus 2 root 5 minus 7.472, which is that. If I do the same thing, -3 plus 2 root 5, I get 1.472, which is that. Right? So the x-intercepts of y equals the thing you're solving for are what you get when you set that thing equal to 0. And so that's the intercepts here. So you can see the relationship between the graph here on Desmos, or any graph, and the x-intercepts, right? And with parabolas, they don't always have x-intercepts, right? Sometimes they, like, here's one that doesn't, right? The parabola opens upward and starts above the axis, so it never gets down low enough to have x-intercepts. And so when you try and solve t squared plus t plus 1 equals 0, you get no solutions. Or I keep saying no solutions. It's no real solutions. You get no real solutions. There are two complex solutions. We could do exactly the same thing here. If I graphed this, we would find that there were two x-intercepts. Okay, that's what I wanted to say about completing the square. So, quadratic formula. This is, in my opinion, the good way, basically, to solve quadratic equations. It's not always the easiest or most straightforward, but it always works, and it's like completing the square, but shorter, basically. So here's the idea. The quadratic formula is this thing right here, this messy formula. X equals minus b plus or minus square root of b squared minus 4ac all over 2. And you can probably find that sung to the tune of Pop Goes the Weasel, which I will not attempt for you. And you should thank me for this, because I am perhaps the worst singer in the world. So where this comes from is, if you were to complete this, so remember what I said about completing the square is that it will solve literally any quadratic equation. Well, here is the most general quadratic equation. This is one where I haven't used any numbers, right? We've just put in a bunch of letters that could be any number. So completing the square will solve this one too. And if you complete the square on this equation, the thing that you get is this, right? These are what the solutions are. So using this is just jumping to the end of completing the square. It's completing the square, but just the formula for the solution to it, right? So you're not spending all that time doing the actual completing the square. You're just like, well, I know how it comes out. It comes out to be this, and you put them in. You put the numbers in, and then you simplify. And that is pretty simple, but sometimes kind of messy, right? It's not totally obvious how to simplify this some of the time. So we're going to do a couple of those. And then that's our third method of solving quadratic equations. So let's solve this one. I got 2x squared minus 5x plus 3 equals 0. And you might notice I've got a is the coefficient of x squared, so that's 2. B is the coefficient of x, that's negative 5. And c is the constant term, that's 3. So I've got a, b, and c are 3. A, b, and c are 2, negative 5, and 3. And I'm going to jam those numbers into this. So I'm going to say x equals minus b, so minus a minus 5. Plus or minus, and I would usually just put 5 there. I'm just writing it out sort of extra pedantically the first time. Plus or minus the square root of b squared. So b is negative 5. Minus 4 times a times c all over 2a. Now, a couple things to note. There's a lot of negatives in it. There's a lot of negatives in this formula. It's very easy to mess them up. Just be really careful. Be really careful that you don't have negative, or that you're getting all the negatives in the right spot. Number 2, this fraction bar, the big fraction bar here, goes all the way left and right. Do not forget to put it under the minus b. People do that all the time. It gives you wrong answers. Goes all the way under there. And then from here, I will just make another plea for you to go slow. Just go really slow. There's a lot of numbers here. There's a lot of negatives. I wrote 2a instead of 2 times 2. And it's really easy to mess them up. So don't. Just be really careful. Like that's the way to go. Just be really careful. Don't be kind of unyielding with yourself on this. It's, it's okay to mess up, but you shouldn't be doing it very often, right? Like, don't beat yourself up if you screw up, but you do want to think to yourself, I know how to do that. I can do that better. Okay, so I'm going to simplify everything. Minus 5 is 5. The square root, negative 5 squared is 25. 25. 4 times 2 times 3 is 8 times 3 is 24. So I have minus 24. Oh, that's nice. All 2 times 2 is 4. So we've got this right here. Go over here. X equals 5 plus or minus the square root. Well, 25 minus 24, I can do that one in my head. That's a 1 over 4. So this says 5 plus or minus 1 over 4. Okay, well, 5 plus 1 is 6. 5 minus 1 is 4. 4 over 4 is 1. Do that. So I'll say that x equals 3 over 2 or 1. There we go. Now, the fact that these came out to be nice, like they're both rational numbers, means that I actually could have factored this if I wanted to. But I didn't really, you don't have to, right? This works fine. I will, at the end, show you how to go backwards and use the quadratic formula to factor, which is actually really nice, right? The quadratic formula just always works. Factoring is a lot of guessing and checking a lot of the time, or, AC method or whatever. And sometimes it turns out not to work no matter what you do. And I'll explain when that happens and what you want to do to use the quadratic formula to help you out there. So there you go. That's how you do the quadratic formula. You identify A, B, and C, you jam them into this big messy formula, and then you simplify things until it looks nice. Okay, let's do another one. All right, so I got x squared minus 3x equals 3x minus 9. So I am going to firstly notice that this works only if ax squared plus bx plus c equals 0. So I have to get everything equal to 0. So that means I'm going to do minus 3x plus 9 minus 3x plus 9. So my left side is going to be x squared minus 6x plus 9, and my right side is 0. And so I'm going to say that a is 1, because there's no coefficient listed. When there's no coefficient shown, it's 1. B is negative 6, and C is 9. So we've got x equals minus b, so 6, plus or minus the square root of b squared, which is 36, minus 4ac, 4 times 1 times 9, all over 2a, so 2 times 1. Right? So this is, that is sloppy writing is what that is. This is 6 plus or minus the square root of 36 minus, well, 4 times 9 is also 36, all over 2. Well, that's interesting. So this says that x is 6 plus or minus the square root of 0 over 2. Well, the square root of 0 is 0. I'm looking for something that when I multiply by itself gives me 0, and obviously 0 will do that. So x equals 6. Now, plus or minus, plus 0 and minus 0 are the same thing, so I don't really have two solutions here, except the 1. And that seems a little strange that such a thing is possible until we go back to Desmos and remember that what we're looking at is the y-intercept of a particular parabola. Y-intercept, the x-intercepts. I'm sorry, I'm saying that wrong. X squared minus 6x plus 9. And this only has 1. Just barely touches the x-axis. Right? And so it does have an x-intercept, but it doesn't have 2. It only has the 1. And that's why we only found one solution. There you go. I don't want to say too much more than that, but it's because this particular thing only has one x-intercept. Now, by the way, I will again return to this, and we're going to see that we could have factored this as something squared. It turns out it's x minus 3 squared. And when that happens, when something is a perfect square that factors, or when something is a perfect square, this happens. You get just the one solution because there's only one x-intercept, and this bit will be 0. So if this bit under the square root is ever 0, that means that this thing is a perfect square and it's only got one solution. Oh yeah, here's all the stuff I put at the end. All right, one more thing. So the last thing I want to show you is how to use the quadratic formula to factor. So I had A couple boards ago, we had x equals 3 over 2 and x equals 1 as our solutions. And I can recreate what that will look like, or I can recreate the formula that comes from, or the equation that comes from. I don't want to use this one. I want to use this instead. Let's say I have, let's say I had this, x plus 3, x minus 5 equals 0. I think it's pretty clear just using the zero product property that we get x equals -3 and x equals 5. Pretty obvious. The reason I bring that up is this. What if I started with that? What if I said, I know that x equals -3 and x equals 5. Tell me a quadratic equation that has those solutions. Well, using the zero product property, you'll be able to say, okay, well, if I know that x equals -3 is one of the solutions, that means that one of the factors has to be x plus 3, right? Because if I put in -3 in there, I would get 0. And if I know that x equals 5, then one of the factors has to be x minus 5. I'll just set that equal to 0, and we're good to go, right? It's very easy to recreate this from that. And we can do that here too. So if x is 3/2, then I can say that I've got x minus 3/2 is one of my factors. And if x is 1, then I can say that x minus 1 is one of my factors. Now, we didn't have any fractions, right? If I multiply this out, I would get fractions. And I would also get just x squared, which is not what we had. What was this? I think I was completing the square on this one. Is that what that was? No. Where was I? I probably just scrolled right by it. And you're watching this video saying, Jeff, you're an idiot. You just ran right by it. Ah, there it was. Yeah. So notice that my original had a 2x squared rather than an x squared. So what that means is that I need to multiply the whole thing by 2. Hello? Can I not? What the heck just happened? Sorry, computer problems. 2. Now, what we can actually do here is take this 2 and distribute it in to get rid of the fractions, which is what people would usually do here. So this is going to be 2x minus 3, right? If I distribute that 2 in, and it only goes into one thing, by the way. Don't distribute it to both. That's double distributing, which we're not doing here. If I multiply this out, minus 3x minus 2x is minus 5x plus 3. There you go. So because I knew what the solutions were, I could recreate the factored form of the polynomial, right? I knew my solutions here, so I could recreate the factored form. So if you get something that you don't know how to factor, you can use the quadratic formula to find the solutions and then recreate the factored form if you want to. Sometimes that's actually very useful. For us, mostly not, but in the future, that is a thing that you can do. Okay, so 3 ways to solve quadratic equations. There is zero product property and factoring. There is completing the square and then taking the square root of both sides, which your book calls the square root property, which is a fine name, I guess. And then there's the quadratic formula. In my opinion, the quadratic formula is probably the best of those. It's like completing the square, but a shortcut, and it always works. Whereas factoring sometimes doesn't work. Some things don't factor, and basically anytime you get something that looks like this, right? There was no way this original equation here does not factor. It doesn't factor in any nice way. You can actually recreate the factored form using these as solutions, but it'll be a big mess. Not something you would ever come up with trying to factor, right? Same thing here. This doesn't factor, and if you spend a bunch of time trying to factor it, you're just going to be frustrated, and it's not going to work. So quadratic formula and completing the square always work. Some people really like completing the square, and you're more than welcome to use it. But quadratic formula is basically the shortcut to completing the square. Yeah, so those are your 3 ways to solve quadratic equations. And that's all I want to say. So I guess I'll stop the video. All right, so I will go ahead and see you guys in the next one.